Hello viewers, we will begin this course with a review of the complex number system, and then we will proceed to study the geometry and then the topology of the complex plane, from where we will start the study of complex functions, which constitutes the study of complex analysis. So, firstly let us review the complex number system. Okay. So, here is a review of the complex number system. So, in here what we are going to do is take an uncritical approach to the complex number system. That is, we are going to assume that the complex number system is given to us, and we will only review the mechanics of how to multiply two complex numbers, add them, etc., and subtract them and divide them, etc. Okay. And then we will see some properties of modulus and the conjugation of a complex number, etc. Okay. So, let me first start with a complex number. Okay. So, a complex number is specified by a complex number is specified by an ordered pair of real numbers a comma b. So, an ordered pair a comma b gives rise to a complex number a plus I b, okay, and is written as a plus I b, okay, where this I here stands for the square root of minus 1. Okay. So, I stands for the square root of minus 1. Okay. So, the complex number system provides for an entity which acts as the square root of minus 1, which is not available in the real number system, and that we denote by I. And given an ordered pair of real numbers, we talk of a complex number a plus b I. Okay. So, we can we can readily take any example like that. 3 plus 2 I is a complex number, okay, and 22 pi plus I root 2 is also a complex number. Okay. So, such things we will call as complex numbers, and two complex numbers are equal a plus I b and c plus I d, okay, are equal if and only if a is equal to c and b is equal to d. Okay. So, okay, and so in particular, okay, so in particular a plus I b, okay, need not be equal to a plus or b plus I a. Okay. And that is why the order in which this pair is given, this pair a b is given, is important, and hence we said that a complex number is specified by an ordered pair. Okay. So, if a and b are not equal, a plus I b is not going to be equal to b plus I a by this statement here. Okay. So, once again I am not going to give any justification here, we are only doing a review of the complex number system. Okay. So, I will pause here to mention that a good reference to a critical approach as to why these rules for complex number arithmetic arose, I will refer the viewer to the book by Tristan Needham. Visual complex analysis by Tristan Needham is a very good reference. So, there a historical perspective is presented, where the evolution of these arithmetic of complex numbers is traced, and also a justification for why the complex number system has arisen, okay, is provided. Okay. So, now we will, owing to this earlier fact here, okay, what we can do is we will define the real part of a complex number a plus I b as a, okay, and the imaginary part of a plus I b as b. Okay. So, often they are abbreviated as a real part of a plus I b and imaginary part I m of a plus I b. Okay. And okay. So, those are a and b. Okay. So, this definition is unambiguous because of the fact that a plus I b and c plus I d are equal if and only if a is equal to c and b is equal to d. Okay. And often we use symbols like or alphabet z, w, zeta, etc. to denote a complex number. Okay. So, that is just a symbol. Okay. And then what we can also do is we can represent, since a complex number is specified by a pair of real numbers a comma b, we can also represent the complex numbers on the Cartesian plane, on the xy plane, like that. Okay. So, if this is the xy plane, an ordered pair a b, for the time being let us assume a and b are positive real numbers. Okay. So, the point a comma b falls in the first quadrant, and this height is your b, okay, and then this distance from the y axis is a. Okay. So, this is the point a on the x axis and this is the point b on the y axis. Okay. And so, a is the real part of a plus I b and b is the imaginary part. Okay. So, owing to this fact, this is called the real axis and this is called the imaginary axis. Okay. So, the y coordinate gives the imaginary part. Okay. So, if x comma y, okay, so x comma y belongs to the plane, okay, corresponds to the complex number x plus I y. Okay. And so, the x coordinate okay, represents the real part, okay, and the y coordinate represents the imaginary part. The imaginary part of a complex number. Okay, when represented on the plane. Okay, and we will call this plane as the complex plane. So, we will call this plane the complex plane often. Okay. This was introduced by the mathematician Argand, and this is also called the Argand diagram or the Argand plane. We often denote the set of all complex numbers by this kind of C, okay, and C is the set of all complex numbers. It is the set of all a plus b I, such that a comma b are real numbers. Okay. So, and there is no repetition in writing a plus b I, a comma b belongs to R, because a plus b I is equal to c plus d I if and only if a equals c and b equals d. Okay. So, that is the set of complex numbers, okay, the set of all complex numbers. Okay. Okay. So, please note that we write a complex number as a plus b I. I also write it as a plus I b. Okay. So, they are one and the same. Okay. I interchangeably use a plus b I and a plus I b. Okay. So, to this end, what we will do is we will make the following table a complex number, okay, and we will use many short forms from time to time. So, here is a small table where I will write a complex number in its short form. Okay. So, a number of the form a plus I times 0, okay, is often written just a. Okay. So, if I just write a real number a and call it a complex number, I am referring to the complex number a plus I times 0. Okay. This is a short form, and a number of the form 0 plus I times b is often written as I b or b I. Okay. Like I said, I am going to write I b or b I, okay, in that form. Okay. And then 0 plus I times 1 is often written as I simply. Okay. This is a specific complex number. Okay. So, this is not a number of the form, but it is a specific complex number. I write it as I. 0 plus I times minus 1 as minus I, and a number of the form a plus I times minus b is often written as a minus I b. Okay. By that I mean a plus I times minus b, where I mean b is that is for the time being assume it is a positive real number. Okay. Then I write this way. Okay. And then so, these short forms should be noted, and we will use them from time to time. Okay. So, one should know what the short form represents. Okay. So, we identify a real number x with the complex number x plus I times 0. Okay. So, for the time being, okay, this plus and dot, okay, are only symbols. So far I have not made any sense of it. I only told that a complex number is represented as a plus I b. So, they are just symbols for the time being. Okay. Later we will introduce operations on, we will review the operations on complex numbers, namely complex multiplication and complex addition, and then we will see that these indeed are the complex addition and multiplication. Okay. So, for now it is just a symbol, and then x plus I times 0 will represent a real number x. Okay. And we identify the real numbers with these kind of complex numbers, okay, which in turn have a short form x. Okay. So, note this short form, a number of the form x plus I times 0 is written as x. Okay. So, notice that the real numbers are not technically the complex numbers x plus I times 0. Okay. But we identify the real numbers as being contained in the complex numbers, and this identification is faithful in the sense that later when we introduce the operations of complex number addition and complex number multiplication, we see that the real number multiplication and the real number addition, okay, tally with the complex number multiplication and complex number addition when we consider numbers of the form x plus I times 0. Okay. So, in that sense the representation of a real number x as the complex number x plus I times 0 is faithful. Okay. But for now we identify these numbers that way, okay. And also in this sense, okay, the set of real numbers are contained in C, okay, in the form of the set A plus I times 0, like I pointed out, such that A belongs to R, okay, contained in set of all A plus I B such that A comma B belong to R. This is the set of complex numbers. Okay. And then numbers of the form I B will be called purely imaginary numbers. Okay. The numbers of the form 0 plus I B are denoted by I B or B I, and we will call them purely imaginary numbers, okay, because there is no real part to these numbers. Okay. So, I want to once again pause here to mention that there is nothing imaginary about complex numbers. Okay. So, it is only that history has given the name imaginary to them, and then that name somehow got stuck, but there is nothing imaginary, they are as concrete as real numbers, okay. And there is a definite arithmetic to it, there is a definite rules of arithmetic, and then they have further properties, as we will see. Okay. So, that you should remember is only a historical thing. So, that yeah, that imaginary numbers is just a historical thing. Okay. And numbers of the form I B will be called purely imaginary. Okay. And then let us review the rules of addition, complex number addition, multiplication, etc. Okay. So, addition or subtraction is as follows. A number 1 plus 3 I, for example, okay, can be added to a number 4 plus 2 I, okay, as follows. So, this is the complex number addition. Okay, addition. We are adding a complex number 1 plus 3 I to the complex number 4 plus 2 I. In the intuitive way, we will add 1 plus 4. Okay, this is real number addition, because the real part is a real number, okay, and then plus I times. Okay. So, once again this times is an artificial thing, okay. It is just a notation for now, okay, plus I times 3 plus 2. So, you add the imaginary parts, okay, which are once again real numbers. So, this addition is real number addition. To get 5 plus 5 I or I times 5. Okay. So, that is the addition. You add x 1, a number complex number z 1 equals x 1 plus I y 1 to a complex number x 2 plus I y 2 to get x 1 plus x 2 plus I times y 1 plus y 2. Okay. So, that is your rule for addition. Okay. And then subtraction is similar. Okay. Subtraction is similar 1 plus 3 I, okay, minus 4 plus 2 I is 1 minus 4. You subtract in the proper order one real number from the other, plus I times 3 minus 2, which gives you minus 3 plus I. Okay. So, z 1 minus z 2 is x 1 minus x 2 plus I times y 1 minus y 2. Okay. And there is complex number multiplication. You can multiply two complex numbers z 1 and z 2, okay, in the following manner. So, normally if you treat these two as binomials, two complex numbers 1 plus 3 I times 4 plus 2 I. Okay. So, that is a complex multiplication. Okay. That is 1 times 4, okay, plus 3 I times 2 I, okay, plus 3 I times 4, okay, plus 2 I times 1. So, this is like a binomial multiplication, okay, and then this in turn, if we treat these as real numbers and multiply, 1 times 4 gives us 4, okay, and then plus, let us collect this these two terms here, okay. We get I times intuitively what we should do is at least by the binomial multiplication, what we should do is, this is 12 plus 2, namely 14 plus 3 I times 2 I should give us 6 I squared. Okay. But I was the entity which was the square root of minus 1. So, I squared should be minus 1. So, using I squared equals minus 1, what we get is, since I squared is minus 1, we get 4 plus I times 14, and then substituting I squared is minus 1, we get minus 6 here. So, this should be minus 2 plus 14 I. Okay. So, yeah. So, using this, what we will do is, we will multiply two complex numbers z 1 and z 2 as x 1 x 2 minus y 1 y 2, okay, where z 1 is like this, z 1 is x 1 plus I y 1, z 2 is x 2 plus I y 2. So, we have the following rule, x 1 x 2 minus y 1 y 2 plus I times x 1 y 2 plus x 2 y 1. Okay, so, that is your complex number multiplication. Okay. So, then we can also divide complex numbers, division. Okay. So, what we can do is, if we have z 2 is not 0. So, we can divide only when we have z 2 not 0, z 1 by z 2, okay, is x 1 plus I y 1 divided by x 2 plus I y 2, okay, is equal to, well, z 2 is not 0, recall, is this, I mean, what this means is, neither, I mean, x 2 and y 2 are not simultaneously 0, okay, x 2 and y 2 are not simultaneously 0. One of them can be, but not both, because the complex number 0 is 0 plus I times 0, okay, which we are abbreviating as 0. Okay. And then x 1 plus I y 1 divided by x 2 plus I y 2 can be rewritten as x 1 plus I y 1 times Well, you will see in a moment why I am doing the following. Okay. I will multiply by x 2 minus I y 2 in the numerator and the denominator. Okay. So, this is this gives me x 1 x 2 plus y 1 y 2, okay, plus I times x 1 y 2 plus I times x 2 y 1 minus x 1 y 2, okay, and in the denominator I get x 2 squared, okay, and then minus x 2 y 2 I and plus x 2 y 2 I cancel. So, I get plus okay, and I times minus I gives me plus 1. So, I get plus y 2 squared. Okay. So, using complex number multiplication on these two, okay, when I multiply them I get x 2 squared plus y 2 squared. Okay. So, then we can divide this into its real and imaginary parts, x 1 x 2 plus y 1 y 2 divided by x 2 squared plus y 2 squared plus I times x 2 y 1 minus x 1 y 2 divided by x 2 squared plus y 2 squared. Okay. So, we are now able to write z 1 by z 2 in the form a plus I b by using this rule, by using this process. Okay. So, notice that z 1 by z 2 when z 2 is not 0 is already a complex number. Okay. There is nothing more one needs to do. All we are trying to do is put it in the form a plus b I, which is how we said we are going to represent a complex number. Okay. So, so this is your rule for division of a complex number z 1 by a non-zero complex number z. Okay. So, these are the rules for addition, subtraction, multiplication and division, okay, and they have the following properties. They follow the following properties, which might be familiar to the viewer from an earlier course on complex numbers. So, firstly z 1 plus z 2, okay, is equal to z 2 plus z 1. Okay, and likewise second z 1 times z 2 is equal to z 2 times z 1. Okay. So, yeah, so these two properties are called commutativity. Okay. So, the commutative property of addition and multiplication. Okay. So, not say that. Okay. So, once again let me go back to these rules and point out to the viewer that this addition etcetera. Okay, I will not point out, but I will not put a pointer there, but this addition which appears here or this addition which appears here, which tells the rule, okay, are real number addition. Okay, additions which the viewer is already familiar with, and this addition here is telling you how to add to complex numbers z 1 and z 2. Okay. And likewise, this multiplication here is the new complex number multiplication, okay, and then this multiplication here or this multiplication here or this subtraction etcetera, this multiplication here, this addition, this multiplication, they are all real number multiplications, additions and subtractions, which the viewer is already familiar with from real numbers. Okay. So, we are trying to define a complex number multiplication in terms of real number addition, multiplication and subtraction etcetera. Likewise, for division, the operations which appear here in this here, okay, within the real part or the imaginary part of z 1 by z 2 are real number operations, which one is already familiar with. Okay. So, having said that, these properties pertain to complex number addition and multiplication. So, so they are both the complex number addition and multiplication are commutative. Okay. And secondly, 3 z 1 plus z 2 plus z 3 So, if you add Z 2 to Z 3 and then add Z 1 to it, it is the same as adding Z 1 and Z 2 first and then adding Z 3 to it. Okay. And so is the case for multiplication. If you multiply Z 2 and Z 3 first and then multiply Z 1 to it, it gives the same result as multiplying Z 1 and Z 2 first and then multiplying Z 3. And so, these 3 and 4 are called associative properties for addition and multiplication respectively. Okay. And 5 Z 1 times Z 2 plus Z 3. Okay. So, multiplication distributes over addition. So, Z 1 times Z 2 plus Z 3 is the same as Z 1 times Z 2 plus Z 1 times Z 3. Okay. Notice that addition does not distribute over multiplication. Okay. So, so it is not true that Z 1 plus Z 2 times Z 3 is Z 1 plus Z 2 times Z 1 plus Z 3. Okay. So, this is multiplication distributing over addition, and then if Z is A plus I b or x plus I y. Okay, let us say A plus I b, okay, then minus z represents a complex number. Okay, so, this is a notation. Minus z stands for the complex number minus a minus I b. Okay. So, then z plus minus z, notice, is 0. Okay. And it is true that z minus z is actually minus 1 times the complex number minus 1. So, it is minus 1 plus I times 0, okay, times the complex number z. Okay. So, so that minus z, although I said is denoted by a plus minus a minus I b, okay, it stands for the complex number minus a minus I b. It is true that minus z is minus 1 times z. Okay. And then 7th one, if z is a plus I b, then 1 by z is your complex number a by a squared plus b squared. Well, you want z non-zero, okay, then 1 by z is the complex number a by a squared plus b squared minus I times b by b squared plus a squared plus b squared. Okay. So, it is the division of the complex number 1 by the complex number z, okay, and then z times 1 by z is equal to 1. Okay. So, there are okay, these are inverse properties. There is an additive inverse and then there is a multiplicative inverse to complex non-zero complex numbers. Okay. So, additive inverse exists for any complex number and then multiplicative inverse exists for non-zero complex numbers. Okay. And you see that with these properties and with these rules for addition, multiplication, subtraction and division, that when you restrict these operations to numbers of the form x plus I times 0, such that x belongs to R. Okay. Like I remarked earlier, when you restrict these operations to this set contained in the complex numbers, okay, you retrieve all your real number operations. Okay. So, this set indeed faithfully represents your real numbers contained in the complex number set. Okay. So, so owing to that fact, okay, you call these numbers, notice, are represented on the x axis, right. These are all numbers whose imaginary part is 0. So, these are represented on the x axis in the complex plane. So, this is called as the real axis sometimes, okay, because the numbers on it, the complex numbers on the x axis represent the real numbers contained in the complex numbers. Okay. And the purely imaginary numbers are on the y axis, okay, in the x y plane. So, this is this axis is sometimes called the imaginary axis, because the numbers on it are purely imaginary. Okay. And now, notice another thing, okay, another thing about this multiplication, okay, that or these rules about addition and multiplication, that a number a plus I b, okay, we have started by representing a complex number in this fashion. Okay. This is indeed the complex number a, okay, which is the plus I times 0, okay, plus the complex number I, okay, times the complex number b plus I times 0. Okay. So, now this is a symbolism, okay, it is the representation of a complex number in the form a plus I b, okay, and this is the genuine plus. Now, this is the complex number addition, okay, and this is the complex number multiplication. When you multiply the complex number I, which is 0 plus I times 1, okay, that is again a notation, okay, and you multiply that to the complex number b plus I times 0, okay, complex number multiplication, and then add it with the complex number rules to a plus I 0, you get back your complex number I a plus I times b. Okay. So, in that sense, this plus and that dot represent your complex addition and multiplication. Okay. And from now on, we will suppress this being a symbol. Okay. We will consider them as genuine complex number addition and multiplication in this sense. So, now we are going to look at the conjugation of a complex number. Okay. So, notice that a plus I b, well, notice first that minus I squared is also equal to minus 1, and so minus I could have equally done the job as I did. Okay. So, with that as motivation, we will look at a plus I b transforming itself as a minus I b. Okay. So, we could have started off by a parallel definition or specification of a complex number as a minus I b instead of a plus I b. Okay. So, owing to that motivation, what we will do is we define okay. So, definition, the conjugate of a complex number z equals a plus I b, okay, is the complex number a minus I b, and is denoted by z bar. Okay. So, z, given a complex number z, z bar stands for the conjugate of the complex number. Okay. And for example, given a complex number, all you have to do to find its conjugate is just reverse the sign on the imaginary part. Okay. So, 3 minus I, and then 1 plus, okay, or 1 minus pi by 4 I conjugate is just 1 plus pi by 4 I. And we will see some properties of this conjugation. Okay. So, firstly, the conjugate of a conjugate is the complex number itself. Okay. So, that is because if you reverse the sign on the imaginary part twice, okay, you get back the complex number. Okay. And the second property is that conjugation distributes over addition. Okay. So, Z1 plus Z2 bar is Z1 bar plus Z2 bar. Okay. And third, Z1 Z2 bar, the conjugate, if you multiply two complex numbers and then you take the conjugate, it is the same as taking the conjugate of the complex numbers Z1 and Z2 first and then multiplying them. Okay. So, the viewer is encouraged to verify these properties by computing the left hand side and right hand side in terms of x1, y1 and x2, y2. So, let me take Z1 is x1 plus I y1, okay, and Z2 equals x2 plus I y2. Okay. So, Z1 plus Z2 is x1 plus x2, okay, plus I times y1 plus y2. Okay. So, that is the complex number addition rule. Okay. So, Z1 plus Z2 bar is going to be the conjugate of this complex number, which is x1 plus x2 minus I times y1 plus y2. Okay. And then Z1 bar is Z1 is x1 plus I y1. So, Z1 bar is x1 minus I y1 and Z2 bar is x2 minus I y2. Okay. So, Z1 bar plus Z2 bar is the addition of these two complex numbers, which gives you x1 plus x2 minus I times y1 plus y2. It is plus I times minus y1 plus minus y2, which is the same as minus I times y1 plus y2. Okay. So, so now you see that this tallies with this. Okay. So, Z1 plus Z2 bar is equal to Z1 bar plus Z2 bar. Okay. So, it is likewise routine to verify 3 and 1. Okay. So, you can just take Z1 is x1 plus I y1, Z2 is x2 plus I y2 and perform the operations in the proper order and verify 1 and 3. So, the real part of a complex number z is equal to the sum of the complex number with its conjugate divided by 2. Okay. So, that gives you the real part, and likewise the imaginary part of a complex number z is z minus z bar by 2i. Okay. So, you can retrieve the real and imaginary parts of a complex number from a complex number and its conjugate. Okay. And on the complex plane, this conjugate is just the reversal of the sign on the imaginary part. Okay. So, if you take a complex number a comma b, okay, then the complex number a comma minus b lies right here. Okay. So, it lies or it is the reflection of the complex number a comma b via the x axis. So, when you reflect the point a b through the x axis, okay, so this distance is of course b and this depth now is b, this is minus b. Okay. So, these distances are equal and you have a comma minus b. Okay. So, that is the representation of a conjugation in the complex plane. Okay. So, that is telling you that, well, it is also clear from the definition that if you reflect a point on the x axis through the x axis, you get back this very same point. So, the conjugation of a real number in the complex plane, okay, is the real number itself. Okay. So, the conjugate of x plus I times 0 is x itself, okay, is x minus I times 0, which is x. Okay. So, conjugate of a complex number is equal to itself if and only if Okay. It is a real number. By that I mean it is a real number contained in the complex number system. Okay. So, we will often call the numbers of the form x plus I times 0 as real numbers, because we will call this real numbers. Okay. That is because we saw that this set of all x plus I times 0 is a faithful representation of real numbers in the complex numbers. Okay. So, from now on we are when we say real number in the context of complex numbers, this is what we mean. Okay. And then the conjugate is equal to itself if and only if it is a real number. I have shown here that if you take a real number, it is equal to its conjugate. Okay. And then here from here you can infer that if a complex number is equal to its conjugate, so the imaginary part is 0. Okay. What that means is it is a real number. Okay. So, it is an if and only if statement. Okay. So, now let us look at the complex plane again, okay, and let us recall that in coordinate geometry we can represent okay, points in the plane also by using polar coordinates. Okay. So, let us say x and y instead of a and b, it does not matter. Okay. So, using polar coordinates we had a representation of this point as r comma theta, okay, where r refers to the length of this vector, okay, this is r, okay, which starts at the origin and well ends at this point x comma y. It is the length of that line segment, and theta was the angle of opening with the positive x axis. Okay. So, in polar coordinates, recall we could represent we can represent a point x comma y, okay, as r comma theta, okay, where x and y satisfy the equations x equals r cosine theta and y equals r sin theta. Okay. So, or if you want to go from x y to r theta, r is given by square root of x squared plus y squared, as you can see from here. Okay, r is the hypotenuse of this right angle triangle. Okay, this height is y and this is x. Okay. So, r squared is x squared plus y squared, or r is square root of x squared plus y squared, and theta, the angle of opening, is given by from this right angle triangle again by tan inverse of y by x. Okay. And this works more generally even if the point is in the other quadrants, okay, or even if the point is on the imaginary axis, okay, where x is 0. Okay. So, there you have to make the appropriate adjustments, okay, and theta is not defined for for 0. For the complex number 0, there is a degenerate triangle. So, this formula will not work. Okay. There r is simply 0, okay, that represents the complex number 0. Okay. For non-zero complex numbers, we have r is this and theta is tan inverse of y by x, okay, except for when x is 0. When x is 0, depending upon the sign of y, you decide whether y is pi by 2 or 3 pi by 2. Okay. And that was polar coordinates. Okay. And likewise, we have a polar representation. So, owing to this, we have a polar representation of a complex number. okay, as x plus I y as r cosine theta plus I times r sin theta. Okay. For 0, we make an exception, we just say r is 0 for 0, r is just 0. Okay. And then here r is equal to square root of x squared plus y squared like above. Okay. Of the complex number x plus I y, okay, and theta is called an argument of the complex number x plus I y. Okay. So, notice that there is a certain lack of uniqueness when you go from the rectangular coordinates to the polar coordinates. Okay. So, by that I mean theta can be more than just one angle, okay, because cosine and sine are 2 pi periodic. Okay. So, any given one value of theta between 0 and 2 pi, okay, any addition of integral multiple of 2 pi to that angle still satisfies x equals r cosine theta and y equals r sin theta. Okay. So, there is that lack of uniqueness. So, the argument, so owing to this, the argument of a complex number, okay, x plus I y. Okay. We define this only for non-zero, not equal to 0. Okay. Write it in one way, is the set of all theta naught plus 2 n pi such that theta naught 0 less than or equal to theta naught less than 2 pi. Okay. So, I will take the interval 0 comma 2 pi closed at 0, open at 2 pi, okay, and n belongs to z, okay, and x equals r cosine theta naught and y equals r sin theta naught. Okay, for some r, here r is unimportant for now, okay, that we know is already the modulus of the complex number, but the set of all such theta naught plus 2 n pi will be called the argument of a complex number. Okay. So, generally when we say the argument of a complex number, we mean this particular set, okay, which is the 2 n pi additions to the angle between 0 and 2 pi, which can be retrieved from this expression tan inverse of y by x, where the complex number is x plus I y. Okay. So, but when we say an argument of a complex number, we pick one value, okay, from this set, and that we generally tend to say is an argument of a complex number. Also, this many valuedness of this argument, we will see has deeper consequences. We will see that during this course. Okay. Theta naught, when restricted to the interval 0 to pi, is commonly referred to as the principal argument of a complex number. Okay. X plus I y, once again not equal to 0. So, for 0 we do not define the argument. Okay. And then we will see some properties of the modulus. Okay. So, we will continue the discussion about argument further on in this course. Okay. There are properties of the modulus that we will see. Modulus of z has a geometric meaning. It is the distance of the point a comma b or x comma y from the origin Okay. So, modulus of z, I did not probably, I just say R is called the modulus of the complex number x plus I y, okay, z equals x plus I y, and is denoted by mod z. Okay. So, it reminds the viewer of the absolute value of a real number, okay, and it tallies with the notion of an absolute value of a real number. Okay. So, by abuse of notation, by abuse of terminology, I might sometimes say absolute value of z instead of modulus of z. By that I mean the modulus of z. Okay. And then the modulus of z satisfies the following properties. Modulus of z is the distance of in the plane, okay, of the complex number z from the point 0. This is the usual Euclidean distance, okay. And then the modulus of z 1 minus z 2 then, okay, is the distance in the plane, okay, of the complex number z 1 from the complex number z 2. Or vice versa. And the modulus of real part of z, the third property, is that this is less than or equal to the modulus of z. Okay. That is clear because the square root of x squared plus y squared anyway dominates the value x itself. Okay. That is the modulus, and that is greater than or equal to x itself. Okay. So, that is that, and likewise it is also greater than or equal to y. So, the modulus, the absolute value of imaginary z is less than or equal to the modulus of z. Okay. I apologize, this is the absolute value. Real and imaginary parts of a complex number are real numbers. Okay. So, the absolute value of real or the imaginary part of z are less than or equal to the modulus. The fourth of the properties is that the multiplication of a complex number by its conjugate gives the square of its modulus. Okay. So, this is an exercise, please verify this multiply number with its conjugate and then try to show that it is equal to the square of the modulus. Okay. And the fifth and one important property of modulus is the triangle inequality. Okay. And this says that the modulus of z 1 plus z 2 is less than or equal to the modulus of z 1 plus the modulus of z 2, and equality holds if and only if z 1 and z 2, okay, lie on the same line passing through the origin. In the complex plane. Okay. In terms of the argument, this says that z 1 and z 2, the arguments of z 1 and z 2 differ by integral multiple of 2 pi. Okay. So, only then the equality holds. So, if and only if statement. Okay. So, this equality holds here in this inequality if and only if the argument of z 1 and z 2 differed by 2 n pi. Okay. So, a proof is easy. Okay. So, a proof of this fact is easy. I will only prove the inequality, and the equality part I will leave it as an exercise to the viewer. The modulus of z 1 plus z 2 squared is equal to the, by the previous property, it is equal to the product of the complex number z 1 plus z 2 with its conjugate, okay, and that gives you the product of z 1 plus z 2 times by the properties of conjugation z 1 bar plus z 2 bar. Okay. So, when you multiply this out, you get z 1 bar plus z 2 bar plus z 2 bar plus z 1 bar. This we know is the modulus of z 1 squared, and this is the modulus of z 2 squared by the previous properties. Okay. And then z 2 bar can be z 1 bar can be seen as z 2 bar conjugate. So, I will write that down, plus this second term can be seen as z 2 bar, it is the conjugate of this term. Okay. So, a number plus its conjugate is equal to the twice the real part, that is by the previous properties. So, this is plus twice the real part of the complex number z 1 z 2 bar. Okay. And then this by the property we saw previously is less than or equal to modulus of z 1 squared plus modulus of z 2 squared plus, well, the real part is less than or equal to the absolute value of the real part, which in turn is less than or equal to the modulus of the complex number z 1 z 2 bar. Okay. And then once again the modulus divides over product. So, distributes over the product. So, this is less than or equal to well, this is equal to 2 times modulus of z 1 times modulus of z 2 bar. Okay. And then the modulus of a complex number is equal to the modulus of its conjugate. So, this gives us z 1 squared mod z 1 squared plus mod z 2 squared plus 2 times mod z 1 times mod z 2. Okay. That is because mod z is equal to mod z bar. Please verify this again. Okay. And this in turn is equal to the modulus of z 1 squared plus the modulus of z 2 squared plus 2 times the modulus of z 1 times the modulus of z 2. Well, the modulus of complex number is equal to the modulus of its conjugate. Please verify this fact. Okay. So, this directly follows from the definition of modulus and conjugate. Okay. And then this is the square of the modulus of z 1. Okay. So, modulus of z 1 plus modulus of z 2. Okay. So, this is the square of modulus of z 1 plus modulus of z 2. Okay. It is the square of these two real numbers. Okay. The sum of these two real numbers. Okay. So, since this modulus of z 1 plus z 2 is a real number, okay, the square of this is less than or equal to the square of this. So, we conclude that the modulus of z 1 plus z 2, since both these are positive real numbers or non-negative real numbers, this and this. Okay. So, we conclude this is less than or equal to modulus of z 1 plus modulus of z 2, which is the triangle inequality. Okay. And the other part of the statement is an exercise to the viewer. Okay. So, with this note I will stop here.